So again, it's sort of like an overarching strategy that we use with rules. So what I want to do is I want to actually start you off. We're not going to prove anything, but I'm going to try to convince you of something by having you recognize some patterns. Okay? We're going to recognize patterns with functions that are so easy that you would naturally say, well, why would you do it? Why would you do it that way? It'd be so much easier if we did it another way. But my idea behind this is, if I can get you to see the patterns with easy functions, then as the functions get a little harder, you're going to be able to still see the patterns, and then we'll get to a point where there are maybe some functions where you wouldn't even be able to see the pattern unless you knew it by looking at the easy and medium patterns. All right, so like there's a method behind this, even if at some point you think, well, that's silly, why would he do that? Which I'm sure you think often. All right, so let's take a look at that function, and let's actually say what the derivative is not. So I need the wrong answer. What is the derivative definitely not?
12.
This is true. It's not 12. Asa?
Definitely not 1 plus 2 or 3.
-1, -2.
No.
Well, x squared.
No, stop. Now you're going to tell me what the right answer is. I want to know what the wrong answer is. What is someone...
It wouldn't be x.
It would be 2x.
It wouldn't be 1 plus 1. It wouldn't be 1 plus 1.
It wouldn't be 1.
So it wouldn't be 1.
Good. It would not be 1 times 1. Betsy says it wouldn't be just the derivative of the first times the derivative of the second. And she's right. It's not 1 times 1. As a matter of fact, without even... I mean, you're already telling me how I should get the right answer. Without even doing that, what kind of function is this? Quadratic. And a quadratic can have what kind of derivative? Linear. Now, 1 is a linear function. It just happens to be a constant function. And a quadratic is not going to have a constant derivative. No, it's not a... Yeah, well, all right, it is linear. It's a horizontal line. Okay, so you all told me I should. All right,
So
distribute.
Plus 3x.
Okay, so now I could take the derivative, and you would tell me it's...
2x.
Okay, now, do you agree that I could write that like this? That's just another way of writing 2x plus 3?
Yeah.
Okay. So, I'm trying to... Like, you'd say, well, that's... Shh! You'd say, that's crazy. Why would you write it that way? And Betsy said, well, should I notice? And I'm saying, shh! You should notice something, okay? And as we do more and more of these, you should see if what you notice continues to hold true, okay? So, let's take a look at another one. All right, the derivative here is not 1 times 1. Definitely not. Okay. As a matter of fact, you would tell me to distribute, and we'd get
X squared plus...
And the derivative there is...
2x plus 10.
Okay, now, some of you might, who saw the pattern before, you might test it out, and you might say, oh, you could write, instead of writing 2x plus 10, you could go to the trouble of writing it as...
X plus 3.
X
Plus 3.
Okay. So there are some people that are looking at this pattern, and they think, at least based on the first few, they can see a pattern. Hold on. We should take a look at something a little harder. Can I stop saying what the derivative is not? Like, are we sure we understand that it's not? Okay. All right, just checking in. All right, so you would tell me to FOIL, and what's that, 13x plus 15? All right, so we know that the derivative is x plus 13. Now, you would have told me, without looking at the derivative, you would have told me that you would have thought that the derivative could be written as 2x plus 3 plus x plus 5, right? Didn't someone say 7? Someone said 7. You made me think it. x plus 5.
Ooh, I think
That doesn't work, though, and that's a bummer. But
It really is. But like then you could just say that if it doesn't have a thing.
we could actually make a very, very small modification
by 2
times what by 2?
times the second. Yeah, that one. So it'd be 2 times x plus 5. So the
So if it say it was 3x.
Ah, shh!
So you're saying, okay,
I'm not saying anything, and that's my whole point. I'm not saying anything. I'm just trying to make you see some patterns. So we actually saw a few patterns based on like the factors, like if the factors were these, maybe somehow they played a part in the derivative. But then we got to a place where it wasn't just the factors that we had. It wasn't the original factors. There was also something that we had to do here. And then, I mean, Betsy made an interesting, without completing it, I mean, what did you say? If it was like what?
3x.
All right, 3x plus 3. So let's take a look at this problem. And let's see how that would change it. Whoops. So we know what the derivative is not. This is going to be what? 3x squared plus 18x plus 15. So the derivative... Whoops. And we might be tempted to say that that's going to be 3x plus 3 plus x plus 5. But that won't work unless we
multiply by
the
3.
coefficient of 3.
multiply that by 3. Does that work now?
Mm-hmm.
Is that true?
Yeah.
All right. I don't want you to say anything because they're going to get harder. If you want to ask a question because you don't understand, no. All right, good. You be quiet, you smarty pants. All right.
Yeah, that's right.
All right.
X cubed.
All right. So x cubed.
I'm gonna have to remember all these. Are these all different rules?
No, he's just repeating the
2x
same rule.
squared plus 5x.
Okay.
And you know what? I'm sorry if I'm saying it too late, and maybe I am. Shoot, I should have said this like 5 minutes ago. Like, if you're writing this down, that's totally fine, but you really don't have to, because we're going to get, all I'm really looking for is for us to, like, see the pattern. Like, if you want to have, like, look, if all of Earth was wiped out and aliens came and found your notebook, like, it would be awesome, because they would see this pattern and they would understand calculus now. But the thing is, we're going to get to a point where we're going to say, oh, this is the rule, and now let's do like 5 practice problems, and those are the important things. So that was my fault. I'm very sorry. All right, that's fine. And you can. There's nothing wrong with that. All right, so the derivative is... Okay, now, we may have said, based on patterns that we've seen before, that the derivative was...
x squared plus 5 plus x plus 2.
Okay, so we may have said that from like the first couple that we were trying to find a pattern with, but that obviously doesn't work.
No, it doesn't.
And there's something here that's missing that would make it work.
You square
A
the
2.
No, you have to square the actual equation because you can't have x squared plus x. You can't add that together to get, you know what I mean, to get x squared. You need to square the entire equation.
If I times it, so Jack said 2, if we times by 2x, does that work?
Yes, that does.
Hold on, let me just check. X squared plus 5 plus 2x squared plus 4x. Yeah, that totally works. So the 2x. Alright, so now it's time to... Alright, that's the question. Don't say it! That's the question. So, like, I mean, we're going to do a couple more, but here there is a 2, and you want to see, like, oh, where did the 2 come from? Here we had a 3, and think about Betsy's question and what she changed and where the 3 may have come from. Here we have a 2x. Where did the 2x come from? Not yet. Alright, this one's going to be hard. No one's going to get it.
Really?
I think so.
Can there be an extra question?
No.
No.
to God.
You battle with stuff.
About to go down.
You listen to Warhammer.
All right, so this is going to be
5x squared, 5x cubed,
Plus x squared
plus 11.
plus 10x plus 2.
okay. So the derivative 15x squared.
Plus 2x plus 10.
Okay, so we would have thought maybe it was like, whoops, based on our patterns, like x squared plus 2 plus 5x plus 1.
You multiply by 15x.
Where do you multiply by 15x?
Because all you're trying to do is find. Oh, you multiply by 2x. All you're trying to do is find the derivative of the original.
Liz, thought or idea?
No.
Oh, you're just stretching. Okay, I thought you were actually being polite. And
Wait, I think I got something.
Well, I don't know. Asa then Jack?
Is it you?
Okay, so wouldn't you multiply by just like, think of it this way, like you're taking the original equation and all you're doing is finding the derivative of the x squared. So you just multiply by 2x.
Where I multiply what? This one by
Yeah,
2x?
No,
All right.
Because in the past.
Hold on. So if that's 2x, we get
That wouldn't work.
10x squared.
It'd have to be 2x
Oh.
squared.
That doesn't quite work. It gives us 10x squared, and here we have 1x squared.
Oh,
I think
It does get us the 2x.
I think I got something.
All right, go ahead. You're up now.
Well, I think for the first one you have to add something to it. You need to put 5 there.
Does that work?
Oh yeah, because then you have to find the derivative of the second.
Hold on.
And that'll give you 10x.
So, Jack says a 5 there would give us 5x squared plus 10x squared. That's 15x squared. 5 times 2 is 10. 2x, that works. Okay. All right. We're ready to figure out what the pattern is. So look, here it is. We started from the very beginning. No, hold on. We started from the very beginning and we looked and we saw that somehow the factors of the function when we were multiplying became terms. So I had x plus 1 plus x plus 2. And then when the functions got more complicated, like 2x plus 3, we somehow had to make up for a 2. Or 3x plus 3, we needed to make up with a 3. X squared plus 5, we needed a 2x. And then finally we got to the place where we had x squared plus 2 and we needed a 2x. And we had 5x plus 1 and we needed a 5. Alright? So it looks to me like there are two products that we're adding together. Zach, what are those products?
Like when you have an x to the only to the first power, the coefficient that's going to go in front of like the product is going to be the same coefficient that's in front of like the x first.
All right, so 5 is like, how does that relate to this?
It's like you take the coefficient before x.
You can do better than that. You're right.
5x plus 1. You take the derivative of 5x plus 1,
But,
and
like,
then
honestly,
you
this
multiply
rule,
that.
like,
I
is
think
cool,
that's a
but,
really
like, I
simple way
don't
of
have to
saying it.
use it.
You do.
Like, just for these problems.
None of these problems you need it for, but
Okay.
if I now give you,
Actual problem. Okay.
so this is, if I now give you e to the x times x squared, that's a product.
Yeah.
And you couldn't do that before, but now we're ready to say, look, if you have a product, the derivative for a product, or the product rule, is the first times the derivative of the second plus the second times the derivative of the first. And I'm ready to put that in a box now. Okay, so the derivative of the product is equal to the first times the derivative of the second plus the second times the derivative of the first. And this is all multiplication and addition, which means it's very, very forgiving. You can mess up the order, and it doesn't matter. As long as you pair the first with the derivative of this other one, right? As long as you take one of them and take the derivative of the other, multiply them together, add it to the one that you didn't do and the derivative of the one you didn't do.
Would I write that? Wait, this really confuses me. Can you just say what it means again?
Yeah. If you have the product of two functions, and you're taking the derivative is the first function times the derivative of the second, plus the second function times the derivative of the first.
Wait, how would I write that not in that notation?
This is probably the best way to write it. Okay. And let's see. Let me do
Is that the other guy? What's his name?
Leibniz. All right. I'll give you. I would never ask you to prove it, but all we did was we really looked at 5 or 6 examples and looked for patterns. Here's the proof, and I also gave you Monday's proof
This is
as well.
just for fun.
Yeah, I mean it's for the doubters out there, right? Someone's going to say, "Yeah, but you know what? I don't know that that's always true." We just looked at 6 examples. Write what? You don't have to write any. You're going to rewrite what I just handed out to you? Oh, okay.
Okay, I know how to write it.
Hmm.
I'm saying there's not enough room.
Uh-oh.
I'm not gonna-
Are we still in the quotient matter?
Yeah, I think so. Quotient rule is Monday.
Oh, okay.
I thought I was getting this document up. I think it is coming up. So let's actually take a quick look at the proof. And while I wouldn't ask any of you to do the proof, and you need to know this. I didn't do the proof. Someone smarter than I did came up with the proof. No. But I can share it with you, and we can follow it along together, even if you don't believe that you could do it. We can at least read it together and follow it. Not having very much luck here. Things are moving a little slower than I had hoped. Not you, the computer. All right. Oh, great. Now nothing wants to open. So how you guys doing?
Well, the Phillies game should still be going on, considering Rollins should be on second and Nash should be on third with 2 outs.
We wasted too many opportunities. It was our own fault.
Yeah, but
I
there's a
know.
lot of missed calls.
Oh my goodness. Now I can't do anything. Oh, okay, sweet. Okay. All right. So I'm going to go back to prove it to the definition of the derivative, and the definition would just say if it's the product, it would be the limit of f of x plus h times g of x plus h minus f of x times g of x all over h. Is that okay?
That's cool with me.
Okay. So here's the clever part. The clever part is that someone said, why don't you subtract f of x plus h times g of x and add f of x plus h times g of x. And if we add and subtract the same thing, what are we really doing? We're adding 0. Is that a problem? No. Who would ever think to add 0 like that? That's sort of clever, right? So here's what we can do. Once you come up with that, let's take a look at the first 2 terms. What'd they do? What'd they factor out?
F of x plus h.
They factored out an f of x plus h. Then the next 2 terms, what'd they factor out?
G of x.
G of x. Okay? Now, they took it and they broke it up into this piece all over h and this piece all over h. It's sort of like the backward of getting a common denominator. They have the common denominator and they split it up. So here we have f of x plus h times g of x plus h minus g of x all over h plus g of x times f of x plus h minus f of x all over h. You know this. What is g of x plus h minus g of x over h?
That's the derivative of g of x.
That's the derivative. F of x plus h minus f of x all over h? That's the derivative. And as h goes to 0, what happens to f of x? It just becomes f of x. Sorry, as h goes to 0, what happens to f of x plus h? It just becomes f of x. and g of x stays the same.
Oh, that's pretty cool.
So
How did they figure out that
I'm
you
telling
needed to add in the atom subtract part? 'Cause
someone's smarter than us, right?
Someone should find
Like, so that, and look, I'm going to reiterate. You don't need to prove it, right? All I want you to do is be able to be convinced that, look, if I had a proof that I had to read through, like, I could do it. It looked overwhelming at first. Like, don't you think it looked a little overwhelming? Right. Yeah. But really, it was just one clever step. All right. And I'm not saying that you were going to come up with a clever step, but if someone does, you can be like, okay, I can follow that. All right. Let's take a look at some problems. All right.
So you just like make one of them F of X and one of them G of X, basically. Like, in your
First
mind.
one's after the last second. Let's see what it is.
All right. Who wants to try out the product rule for the first one? Jack?
Alright, I think it would be, you split it up and it would be 2 times 3 to the x,
Where are you getting the 2 from?
the power or the derivative of x squared.
What's the derivative of x squared?
So
Try again.
2x up.
2x. So the derivative of the second times
The derivative of the first, which
Oh,
times f of x
times the first. So there's the derivative of the second times the first plus
plus, and then it would be the derivative of the first, which would be ln of 3 times 3 to x, and then times x squared.
Okay, so just to recap, this is the derivative of the second. This is the first. This is the derivative of the first. And this is the second. And you can see, like, Jack did a little different order, but it doesn't matter. That's the right answer. Right? So you can do a bunch of different orders. When we saw the pattern, we did one way of doing it. When we showed the rule, right, we did first derivative of the second plus second times the derivative of the first. Okay, but multiplication and addition are forgiving. Okay, so the order for addition, it doesn't matter if you add a plus b or b plus a, and the order for multiplication doesn't matter. If you multiply ab, that's the same as ba. All right, who's up next? Gabby?
Would it be 8? Would it be 18 x?
Sorry, hold.
Times x squared plus
Not yet. 18x to the 17th plus 2. So the derivative of the second times
x squared plus 5 plus 2x times x to the 18 plus 7.
Okay, so the derivative of the second times the first plus the derivative of the first times the second. Okay? You could have FOILed this out, right?
Yeah.
We could have.
How would it take them?
Okay. I don't know, because it's not like something raised to the 18th power. I think, well, whatever. You have options now, which is nice. All right, Gabby, who's up for the next one?
Okay, so the ln of 2 times 2 to the x
All right, so the derivative of the second
multiplied by e to the x.
times the first. There's the derivative of the second times the first.
Yeah. So then you'd add e to the x
The derivative of the first
multiplied by 2 to the x.
times the second.
Oh wait, that's just like funny.
It has itself in the answer.
Yeah.
Okay. All right, Asa, call on someone.
Kaylee?
E to the X times E to the X.
All right, so that's first times the derivative of the second, or is it the second times the derivative of the first? I don't know. Plus
E to the X
times the derivative of the first times the second, or is it the other way around? I don't know. I don't know. What is that? That's what?
e to the x
E to the, when we multiply, e to the 2x plus e to the 2x. And what's that the same as?
2e to the 2x.
Good. Okay.
So I'm gonna ask of you.
Holy moly. Something to close to this.
All right. I feel good about that. So do you see, I don't know if what you want to say. Do you want to say that the product rule is a new rule, or is it like a strategy that you use with rules?
I think it's a rule.
It's a rule. Okay. So it's called the product rule. We have the product rule.